So a multi-step reaction. This is where we kind of start to add. You've learned about Grignards, you learned about oxidizing things. Now it's kind of adding those two things together in two separate steps. So in the first thing we have, this is formaldehyde. It's an aldehyde with two H's. That's formaldehyde. And we have a methyl Grignard, just one carbon. So I numbered the atoms, 1, 2, 3, for no particular order or reason, just to make sure I don't lose them. If I see a Grignard, you should automatically think basic conditions, reactive nucleophile. That's a C-, that's a carbanion. You see a carbonyl, you should see the carbon 1, the carbon of the carbonyl is electrophilic because it's double bonded to oxygen. So what's going to happen is that we're going to have the Grignard react with the formaldehyde. So the electrons in that bond are going to go. We're going to add in, break that pi bond. That's that addition step. We're going to make a tetrahedral intermediate. All right, the Grignard, the MgBr, just to make sure we're balancing our charges, is along for the ride. Just make sure our numbering is good. 1, 2, and there's 3. So we made a new carbon-carbon bond between 3 and 1. We have a tetrahedral intermediate. What do we ask ourselves when we have a tetrahedral intermediate? Do we have any good leaving groups? Do we have any good leaving groups here? We have 2 hydrogens and a carbon. Nope. So that means we go on to the next step. The next step is protonation. Protonation. So we're going to end up with an alcohol. We're going to end up with a primary alcohol. And this is the intermediate we have. All right? A primary alcohol. So you got to get to that point first. So now that you have the primary alcohol, now you start thinking about the next step. The next step is PCC. So you got to remember what PCC does. That's that less reactive oxidant, right? Oxidants take away hydrogens, make more bonds to oxygen, oxidizing it. So we're going to lose one of these H's. And so the final product we're going to end up with is just an aldehyde. And because it's PCC, we stop at the aldehyde. We don't make the carboxylic acid. 2, 1, 3. If we wanted to make the carboxylic acid, we'd use Jones reagent or some sort of chromium species, or KMnO4. So in this one, we're having an alcohol. Again, it's always important, I think, to identify what these are. This is a primary alcohol, even just to remind yourself what you're dealing with. And you're reacting with PBr3. So why do we do these? So the whole point of these is to take this OH, which is not a very good leaving group, and turning it into something that is a good leaving group. We're activating it, right? We're trying to, at the end of the day, we're just trying to substitute out the OH, right? So there's 4 different ways we're going to do that. PBr3 is nice because it's a little bit less, less reactive in theory than HBr, or doesn't react as much with stuff as HBr does, right? HBr can react with alkenes. You saw that a long time ago, right? HBr is a really reactive acid, strong acid, so that's going to be tough to deal with. So PBr is kind of a nice reagent to use because it focuses only on being reactive with that alcohol versus something else. So what happens? What's my electrophile? What's my nucleophile? You always ask yourself that for each step of the way. The alcohol is a good nucleophile, the OH, the electrons and the oxygen. Phosphorus, you might not think about it that much as being a good electrophile, but right, it's bonded to 3 bromines. Right? And again, these are a little weird, right? Because people were worrying about phosphorus and sulfur a lot. So it's like an SN2 reaction here, right? Where we literally just kick out the bromine. Now some might say, well, wait a second, that's a pretty substituted bromine. That should be hard, right? SN2, backside attack. But then you got to remember, where's phosphorus at in the periodic table? Right? It's below, right? It's a big one. It's below nitrogen, right? It's down a row, so it's a much bigger element. So some of those rules that we love and adore for the top row don't work for oxygen and things like sulfur. So we can do an SN2 on a phosphorus. So what did that accomplish? That just turned make sure we balance our charges. We broke a bond to phosphorus and bromine. There should be a plus charge where? Where should I have a plus charge? On the oxygen, right? The oxygen lost a lone pair, or using a lone pair in a bond now. So that should have a plus charge. You have Br minus to balance our charges. Renumber our atoms, 1, 2, 3, 4. Now the bromine's floating around, and you notice, right, just like we did with HBr, remember you protonated an alcohol, and that made it into a water, like a good leaving group there? This is the same idea. This is also a really good leaving group. Right? The oxygen now has a plus charge. That makes this a good leaving group. Now the bromine can come back in and do an SN2 reaction. Another SN2. And that gets us to 2, 3, 4. H, phosphorus, and the bromines, balancing my charges. This is oxygen 1. And I believe I mentioned on the video that these PBr3s could be used for delivering 3 bromines. But I'm not worried about you showing the final, like keep doing it with the same bromine. I just want you to show it to me once. Right? So you show it to me once. Now, this gets more complicated, and we'll talk about that a little bit more. Right? It's nice, this is the primary alcohol. Can a primary alcohol be RS? No, because there's 2, right? To be RS, to have a chiral center, you must be sp3 hybridized and have 4 different things bonded to you. This carbon 2 is sp3 hybridized. Good. Is it bonded to 4 different things? No, it's bonded to 2 hydrogens. So it can't be a chiral center. Secondary alcohols can be. Are they always? No. Right? So you got to be able to recognize chiral centers still. Right? I'm not asking you to do R and S, but you have to be able to recognize chiral centers. sp3 hybridized, 4 different things bonded to it. And you got to know that when you do an SN2, what happens in an SN2 reaction? You get inversion. Right? It doesn't really matter in this first step because we're not worried about PBr3, right? Phosphorus has the same things bonded to it. So even though it's an SN2, there's no really inversion there. When you do the inversion in the second step, though, if this carbon 2 was R, at the end it would have to be S. Right? So you've got to be able to recognize those things. All right, so alcohol, SOCl2, pyridine. What do we end up with as a product? So what do we know first of all? Right? We know that this is a secondary alcohol. What do you know from SOCl2? We know no carbocation rearrangements. Right? We know primary and secondary alcohols only. That's the only thing it works with. And we know it's going to do an SN2 reaction. Right? We're going to get some sort of inversion. So I see SOCl2. And I know that. You should those things should like pop in your brain before you even look at anything else. What do I know about SOCl2? No rearrangements, primary and secondary only, inversion, SN2. So the product here then, without having to do the mechanism, I see this OH as wedged. I know that these are all activation of alcohol methods. That means I'm turning this into a good leaving group. That means the OH is going to leave, and in this case, Cl is going to come in. So I can just, without, doing R and S or any of those things, I can just say, okay, that's it. I've done an inversion here. The H was wedged, it was going back, now it's coming forward, and the chlorine has replaced it. That's an inversion. I don't know if this is RS, this is R, now it's S. I'm not asking you to know that yet, right now. But you should be able to look at this and be able to draw the inverted product without having to do R and S. You can always do R and S to check to make sure you did it right. Nothing wrong with that. But that's the final product here.